Hello, this is chapter 5, question number 4. I'd like to do this as an example. It says, do heavier people burn more energy? It says, we have the data on the lean body mass and resting metabolic rate for 12 women who are subjects in the study of dieting. Lean body mass given in kilograms is a person's weight leaving out all fat. Metabolic rate in calories burned for 24 hours is the rate at which the body consumes energy. Okay, so here's the data. Let's take a quick look at the data here. And just af after a quick scan, what preliminary conclusions can we make? We have the lighter people, like 36.1 kilograms, 33.1 kilograms. We can see that they, in general, they have lower metabolic rates. Um, we can see that the heavier people, like the 50.6, has a higher metabolic rate. Another one, another higher mass, higher rate. So it does, after a quick glance, it does look like there is some sort of relationship between these two. Let's go ahead though and make a scatter plot out of this, because the only way we will really know for sure is by making a scatter plot and finding the correlation and so on. And so for the x-axis, let's call mass, we'll call that x. The rate, we'll call that y. Now, to decide what's x and what's y, usually the first column is x, second column is y, but the better way to think about this is what's the explanatory variable and what's the response variable. You could think of the mass as somehow explaining what the rate is going to be. So therefore, the mass is going to be the explanatory variable. Okay, so for the x-axis on our scatter plot, we need to decide how to scale the x-axis. So the numbers for the mass range from, looks like, about 33 kilograms up to about 50 something kilograms. And so let's just start at 30. And how about I go by 5? So here's 30, 35, 40, 45, 50, 55. Is there anything higher than 55 in this raw data? No, nothing's higher than 55. Okay, for the y-axis, that's the rates. The numbers range from the low 900s to 1500s. So how about we start at 900 right here and go by hundreds. So 1,000, 1,100, 1,200, 1,300, 1,400, 1,500, and I'll go ahead and write down 1,600 as well. All right, let's go ahead and plot some points. So the first point, mass is 36.1, rate is 995. So that's 36.1, right about there, and rate 995. It's almost 1,000. So that point is right about there. And it's fine just to estimate these points. Now I'm going to fast forward this and just put in all the points. You get the idea. So to save a little time, I'll just put all the points in. Okay, so I just finished making the scatter plot, and yes, indeed, you can see there is a positive trend as the mass increases, the metabolic rate increases as well. And if we wanted to imagine a line going through these points, that would probably look, a best fit line would probably look something like this. But I don't want to draw any lines yet. All right, let's answer the question. So part A, make a scatter plot. Okay, we did that. Great. That shows how the metabolic rate depends on body mass. There is quite a strong linear relationship, as we can see from the scatter plot, with correlation R equals 0.876. Okay, thank you, Mr. Moore, for doing that calculation for us. So let's just copy that up here. R equals 0.876. Now, we know how to do that calculation. It's a rather time-consuming calculation. Usually, you would download the data to Excel or some other software and use some command to calculate that for us. But They did it for us, so one less thing that we have to worry about for this problem. Okay, now part B. Find the least squares regression line for predicting metabolic rate from body mass. Add this line to your scatter plot. Okay, this is where all the formulas that I talked about in the earlier lesson come into play. If you remember those formulas here, let's write these down here. We have the basic formula for a least squares regression line is y hat. Remember, y is the predicted y, so we need a hat on top, equals a plus bx. That's the way the author writes it in the book. These are early in chapter 5 if you want to refer in your book. And then the slope, b, is equal to r times the ratio of the standard deviation, so sy over sx. And then a equals y bar minus bx bar. All right, so we can see here, in order to do these calculations, first we need to know the standard deviation of the y's, standard deviation of the x's. We need the mean of the x's and mean of the y's as well. So we have to do some number crunching here. So we can take all our raw data here, take all the x's, put them into a calculator or download them off the textbook website and use Excel or some other means to get the mean and standard deviation of all these x's. Same thing with the y's. We need to get the mean and standard deviation of all these y's. So I went ahead and just downloaded these to an Excel sheet right here. Let's go ahead and I'll just use the standard deviation and the average commands here. So I'll just type average equal average of A2 to A13. Okay, so there's the mean of the mass. Let's do the standard deviation as well. Equal sign standard deviation A2 to A13. Okay, so there's the mass. Let's label these here. This is the mean. This is standard deviation, and let's just write mass up here so we can keep track of all this. Okay. Also, we need the mean and standard deviation of the rates. A nice thing about Excel is you can just grab those two cells. There's a little dot in the corner. You can just click it and copy it over. And then it gives you, it just recopies the commands there. So we have your average, B2 to B13. That's the mean of all the rates. And we have the standard deviation, B2 to B13. That's the standard deviation of all the rates as well. Okay, so thank you, Excel, for doing the hard work for us here. So now let's move this over to the side here, and let's write these numbers. Let's copy these numbers down here. So x bar is just a moment here. X bar one more time is 43.03. That's probably good enough for rounding here. 43.03. The standard deviation of the x's, let's go back to our Excel sheet again here, is 6. I'll round this here. How about 6.87? All right, 6.87. All right, standard deviation. Excuse me. The mean of the y's, the mean of the rates, is 1235.08. So 1235.08. And then the standard deviation of the y's, the standard deviation of the rates, is 188.28. Okay, let me just double check here, make sure that I copied all those down correctly. Let's just move this in here. Okay, so 43.03 is the mean of the mass, 6.87 is standard deviation, the rates 1235.08 and 188.28. Okay, looks good. Okay, so now all you do is you just take those values right here and just plug them into the formulas, and you get your slope and y-intercept. So first, you have to compute the slope. And so b equals r uh, times standard deviation of y divided by standard deviation of x. So r was given to us. R is 0.876. So now I'm going to have b equals 0.876 times standard deviation of y, 188.28, divided by standard deviation of x, 6.87. Remember where this formula comes from. Basically, if r was equal to 1, then the slope of our line, if x goes up by 6.87 by one standard deviation, then y goes up by 188.28. Now we have a limiting factor, so to speak. We can have to multiply by r as well. So do this calculation. Just get out a calculator, or if you're using Excel to download your data, you might as well use Excel for this. I think I'll go ahead and just use a calculator. I'll just use the computer's calculator here. Okay, here it is. So just type 0.876. It is 876, isn't it? Let's double check here. Yeah, 876. That's right. 876 times 188.28 divided by 6.87. Okay, so 24 points. How about 24.01? Round it off. Okay, there's our slope. And what does slope mean? Well, it's rise over run. It basically tells you every time, let's go back to our raw data here. In general, anytime x goes up by 1 kilogram, then y goes up by about 24 calories per 24 hours, period.